In the first part of this module, we've talked about how we get fossil fuels, what they are, how we put them to use, and how much of them we have left. There are some problems, obviously, with the dwindling supply. So even if fossil fuels had zero environmental impact, we would be facing a real challenge in terms of making sure that we don't run into an energy crisis with a gigantic demand for energy running up against a vanishing supply. In this final part of Module 4, we'll be talking about the environmental impacts of fossil fuels, and in particular, we're going to be talking about uh, pollution, primarily air pollution, but other types as well. So first, we just need to define what we mean by pollution. So pollution is just any substance that's introduced into the environment that is harmful in some way. And this is not an exhaustive list, but some common pollutants are small particles, and we'll talk about how they can be hazardous in a few minutes, various molecules that mix in the atmosphere, such as sulfur dioxide, carbon monoxide, nitrogen oxides, and ozone that are hazardous when you're inhaled. They can also have other uh, deleterious environmental effects on plant life and as well as animal life. Then there are just various toxic compounds. Volatile organic compounds are carcinogenic. Heavy metals are health hazards as well. And these are things, some of which are going in the atmosphere, volatile organic compounds, but mercury is going into groundwater and is taken up by fish, which then makes it into the food chain, and it gets sort of concentrated as it works through the food chain. Carbon dioxide is listed last on this list. Carbon dioxide, of course, occurs naturally in the atmosphere at a small level. It was about 0.025% of the Earth's atmosphere prior to the Industrial Revolution. It's now at about 0.041% of the atmosphere. And small amounts of carbon dioxide, we're breathing it out, plants are breathing it in all the time, is not directly harmful to an individual's health. But of course, as we'll see in the last part of the course, carbon dioxide is a greenhouse gas that affects the climate, and that in turn then affects ecosystems. In the United States, there's been some debate, political debate, about whether or not the Environmental Protection Agency has the mandate and authority to regulate emissions of carbon dioxide, which basically depends on whether or not it's considered a pollutant. So let's start off with pollutants that go into the air, and we're going to break this into two broad categories: particulates and gases. So particulates means small particles, and small particles, we're not talking about necessarily what the composition of those things are. It does matter what the composition is, but primarily the hazard of them is just that these are little tiny solid particles that you can inhale and go into your lungs, and then they produce lung damage and they don't come out. Big things that you inhale don't go very deep in the lungs and you can cough them out, but very small particles, smaller than about 10 microns, get inhaled into the deepest tiny air pockets of the lungs, and they don't come out, and they do permanent and cumulative damage to the lungs, which can ultimately be fatal. For point of reference, hair is about 100 microns in diameter, so these are particles smaller than about a tenth of the width of a human hair. And as another point of reference, the particles in, say, smoke are typically about 1 to a few microns. So if you're burning coal, as an example, part of the exhaust that comes out from that combustion are going to be little tiny particles. And so we want to remove those particles instead of just sending them into the air, because they're so small that they'll stay suspended in the atmosphere for long periods of time and can be inhaled. And so we want to remove them from the exhaust. So we're going to show two devices that help remove particulates from the exhaust. This one is a cyclone separator, cyclonic removal, and the sketch shows how this works on the left-hand side of the figure. the exhaust air from burning your gases goes into this cyclone, and the air is warm and wants to go out the top, and the shape of the cyclone forces that air that's coming in at a reasonably high speed to spiral around. And as it spirals around, the particulates will smash into the walls because they've got more inertia than the gas. And so they run into the walls and then fall. And so you just have this rain out of the small particulates to the bottom, and the gases that are now free of those particulates escape out the top. Another device pictured here and with a schematic that can be used to reduce particulates is using electrostatic force. So the diagram shows two big collection electrodes, and they are charged positively. So it says positive charge down there with wires schematically going to those two large plates. You put a positive charge on those, and you run your air in between those two plates. And in the middle of that, you've got some electrodes, wires, that you have charged negatively to and with that negative charge in between those positive charge plates, electrons are emitted from that negative electrode. So these are the small negatively charged particles and atoms. They come showering off, flying off that negative discharge electrode, and they hit the dust particles, these fine particulates that are in the exhaust gas. And then those particulates now have a negative charge, and as we've seen, unlike charges, opposite charges attract each other, so the negatively charged dust gets attracted to the positively charged plates on either side. So the particles run into the plates, again, smack into them, and then they neutralize when they make that contact and they fall down. So those are two ways that you can reduce the amount of particulates in the exhaust gases. Of course, in this example, it's taking energy to power those electrodes. So it adds a cost, and it reduces the efficiency of the power generation plant. Now let's talk about non-particulate emissions. So we mentioned sulfur, carbon monoxide, ozone. Sulfur emissions particularly are a product of burning coal, much more so than burning natural gas. So coal burning power plants release a lot of sulfur just because there's sulfur in coal. And so you get sulfur oxides, sulfur combined with oxygen as a result of that combustion. SO2 is not good for the health, and it also reacts with water in the atmosphere to form sulfuric acid, and so it acidifies the rain in the vicinity of these coal burning power plants. And so the map here is showing the acidity of rain in the United States. The smaller numbers, which are the greener values on this plot, correspond to more acidic values for the rain. And for algae and things that are uh, dependent upon that algae to survive. So there's an ecosystem hazard as well as a health hazard. And the map just shows that there's a correlation between where we have coal burning power plants and where we have very acidic rain. There are technologies to remove sulfur from the exhaust of a power plant. Those involve chemical scrubbing. So you run your dirty gas through a scrubber, which is a device that's got various other compounds and molecules in it that reacts with the sulfur oxides before they come out the other end. Another gaseous air pollutant is carbon monoxide. Remember that we're burning hydrocarbons. That means we're reacting hydrocarbon molecules with oxygen. So one of the products of those reactions is carbon monoxide, CO. CO, unlike CO2, is directly poisonous to people. It binds to the blood cells where oxygen does, and it's odorless, and people die from carbon monoxide poisoning from accidents where more in the north, where there are home heaters that are burning natural gas to heat homes. If there are leaks of CO from the exhaust of those that build up in the house in the winter, uh, you can uh, basically suffocate from that CO. So it's definitely a toxin, and this chart just shows where the production of CO comes from. Half of it from road vehicles and an additional 20% from non-road vehicles. That would include things like aircraft or farm equipment. Another gaseous air pollutant are nitrogen oxides. So we've got a pattern here. An element combined with oxygen. These are our pollutants in the air. Sulfur with oxygen producing acid rain, carbon monoxide, which is toxic, nitrogen oxides, which are also a contributor to acid rain, and a cause of smog, which we'll explain shortly. So one of the ways that the atmosphere helps to keep itself clean, or at least keep the lower part of the atmosphere, is through convection. That's a process we've previously described that transports heat from near the surface to higher up in the atmosphere. The warm surface of the Earth, heated by the sun, warms the air near it, which expands and rises. And that can take some of the pollutants that are present near the surface where we are having our power plants and our cars and our trucks putting out these pollutants. And so convection and local weather helps disperse at least some of these pollutants and keep them from being very concentrated. There's a condition, however, where that dispersal doesn't occur, and that condition is called a temperature inversion. Normal conditions are shown on the left-hand plot here, where the atmosphere is cooler as we go up in altitude, as indicated by the blue line, and the warm, polluted air that's rising also gets cooler, but not quite as quickly as the surrounding atmosphere, so it continues to rise to the top of the troposphere. The plot that's shown here is just going up a couple of miles, and the troposphere is 7 to 10 miles high. The temperature inversion takes place where either the rising air cools off quickly and or the atmosphere locally is not getting cooler as we go up in altitude, at least for the first couple of kilometers, as shown in the right-hand plot, where that blue curve showing the atmospheric temperature is getting warmer as we go up from the surface. And what that does is where those points cross, where the red curve and the blue curve cross, convection stops, because now that warm air is no longer moving into a cooler region, it's moving into a warmer region, so it stops rising, and that then traps the polluted air close to the ground. So temperature inversions are a weather phenomenon that lead to local air pollution hazards, and they can be particularly bad in certain sort of geographic locations like valleys where there's no wind to carry things away either. So the photos here show the smog buildup in a temperature inversion condition in the lower figure compared to normal atmospheric conditions in the upper figure. So what is smog? Smog is a mashing together of the words smoke and fog, and it is a combination of particulates and gases. And so what happens is that some of the polluting gases that are produced from primarily automobiles get trapped by a temperature inversion and mix with water, microscopic water droplets in the atmosphere to produce this trapped layer of very polluted air called smog. Uh, there's not a lot that can be done to reduce that except reduce the amount of emission of these polluting uh, um, molecules. So burning things cleaner. And so we try to burn the gasoline in our cars cleaner. Catalytic converter is a device that removes some of these devices. And the figure on this slide just illustrates how it's tied to car usage. So this is in Los Angeles in January, and you can see that nitrogen oxides, which are the red dashed line, and the small particulates are concentrated around the morning rush hour, and ozone peaks a few hours later. Ozone is three oxygen atoms together. It's a irritant to the lungs. It doesn't last very long in the atmosphere. I create a whole bunch. If I just wait, it dissipates. As you can see, this red curve spikes and then goes down. But ozone can be very hazardous to health, especially for people with some respiratory issues already. But it's a local temporary phenomenon. It's not sort of like a global change phenomenon. And ozone is produced by sunlight interacting with the other pollutants that are emitted by cars. That's why it's called a secondary pollutant. It requires sunlight acting on the things that are produced from the cars. It's not directly emitted from the cars. And then we mentioned mercury as an example of a heavy metal pollutant. And you'll remember earlier we saw a map of where coal burning plants are in the United States. And again, here we see the mercury concentration in fish in the United States is high and is tracking with where coal burning is most prominent in the United States. Other environmental impacts of fossil fuels are not just the nasty products that are produced when we burn it and emit those into the atmosphere and into the water supply, but also just direct impacts such as shown here. Coal mining obviously is directly devastating this local environment of this hilltop. And then there can be accidents with drilling for and transporting oil. So this is one example from 2010, which is the worst oil spill in history. There was an explosion and over 4.9 million barrels of oil gushed out of the broken drill at the bottom of the Gulf of Mexico, on the floor of the Gulf of Mexico, into the Gulf of Mexico over a period of weeks. And I don't need to probably tell you that obviously all that oil is not healthy for the ecosystem of the Gulf. In addition to that kind of accident, the Deepwater Horizon accident, which was an oil drilling accident, there are oil spills from tankers that transport oil. So this plot is showing the amount of oil spilled in boating accidents from tankers. And there was a famous accident called the Exxon Valdez many years ago. And following that accident, new measures were put in place to keep those tankers safer by having double hulls. And so you can see there's been a dramatic drop in the amount of oil spilled from those tanker accidents between the 90s and the present time. And just for reference, just to go back to the Deepwater Horizon drill, the amount of oil spilled here, 5 million barrels. This is in tons, but I've worked out the conversion. The amount spilled in that Deepwater Horizon is off the chart on this particular chart. It's 2 to 3 times higher than the top of this chart. So that one drilling spill dwarfed the worst year of tanker spills, and this is just to remind us that it has obvious devastating environmental impacts. And another type of mining for tar sands. This is the most abundant type of oil found in Canada, which is the dominant repository of oil in the North American continent. So this chapter finishes just with a discussion about how to mitigate some of these environmental impacts. The Clean Air Act uh, specifies things that should be controlled and the amount of them that are allowable, and requires cars and industry to reduce emissions below certain levels. And so you specify those standards over time, and this was first implemented in 1963. And over time, some of those standards then increased to gradually improve the quality of air. And you can see now the actual data. This is emissions of the different uh, uh, hazardous and dangerous compounds over time from 1970, a few years after the Clean Air Act was passed, to the late 2000, just before 2010 in this figure, and you can see that it worked. So even though the number of cars increased dramatically, our energy use increased dramatically, the amount of pollutants, this is total amount, not per person, the total amount of pollutants being put out in the United States did drop by roughly half over that period of 40 years. Looking specifically at nitrogen oxide emissions, which are coming from vehicle exhaust pipes, you can see the various standards for those changing over time, and those get implemented by automakers, and then do end up improving the quality of the air. And I can tell you from personal experience, I fly to Los Angeles a lot for my research work on space missions going to the Jet Propulsion Laboratory, and I started going there regularly in the late 1980s, and the air quality I can see when I'm there, but also landing and taking off and sort of flying through where the inversion layer would be. The air in Los Angeles, even though it's much more populous, has far more cars now than it did 25 years ago or so when I first started. The air is so much cleaner, to the point that when the first few years I went there, I didn't even know that there were mountains near Los Angeles. And then the air cleaned up, and I was shocked. It's like, oh my gosh, there are mountains right there. So that's just to say that it is possible to mitigate the environmental effects, and it requires regulations and enforcement of those regulations. And when that happens, then both the air and the water are kept cleaner.